So today's video is about solving systems of equations with a specific method, graphically. So just as a reminder, there are three different methods that we're going to study about solving a system of linear equations. Today we are only focusing on graphing, but again there are other methods that we'll get to, but today's video is just about graphing. So just the conceptual idea is we already know that when we have a solution to a system of two equations, it's the ordered pair that satisfies both of them. So like as a quick example, if I did something like x plus y was equal to 3, and then something like 2x plus y was equal to 5, I would know that the point 2, 1 is the solution, because if I checked both of them, 2 plus 1 is equal to 3, so it satisfies the first, and then 2 times 2 plus 1 is equal to 5, so it satisfies the second. That's what we already know. So our new material for today is when we do this graphically, we're going to look for the point where those two lines on the graph intersect. So that will bring up kind of like an overall process for us to do today. When we're trying to solve a system of two linear equations on a graph, what we should do is obviously graph the first one, and then we should graph the second equation. And then we just want to see the exact point of intersection. And as always, when we're done with that, we should check our answer to make sure that we are right. So this would be our general idea when we are solving a system of linear equations graphically. Graph them both, see where they touch, and then check our answer. So like here's just a quick little introduction. I want to solve both of these equations graphically. We're going to use technology to do so. So we are first going to focus on this one here. So negative 4x plus 5 and y equals 2x minus 4. Just to see conceptually what we need to do is we need to graph both of them. So I'm going to pull up my Desmos graph here. So our first equation is y equals negative x plus 5. So I've accurately graphed the first equation. The second equation is y equals 2x minus 4. Y equals 2x minus 4. And then according to our list of steps, I want to see where they touch. So it's very clear that those 2 points touch, or these two lines touch right there at the point 1.5, negative 1. So the solution to that equation would be 1.5, negative 1. And if we check our work in both of the equations, we'll see that it's true. So if I plug in y as negative 1, means negative 4 times 1.5 plus 5. So we get negative 6 plus 5, so it is equal to negative 1, so it makes the first equation true. And we have to make sure that the y value of negative 1 would equal 2 times the x value minus 4. And we do see that 3 minus 4 is equal to negative 1. So it does make both of them true. Let's do another example on the other side. Let's see where these two systems touch. What is the solution to this system of two linear equations? So again, we're just going to use a graph for this one. So 2x plus 3y is equal to 8. So we'll graph that one first. And then the second equation in our system was x minus y equals 4. So I graphed both lines accurately. I'm going to look to see where they touch. And according to Desmos here, they touch at the point 4, 0. So that would be the solution to my system of equations. The point where these two lines touch is the ordered pair 4, 0. Now to make sure that it is the solution, we have to check both of them. So I plug in x for x, and I plug in y for y. I got to make sure that 8 plus 0 is equal to 8. So it satisfies the first equation, and we just need to make sure that if I take the x value of 4 and subtract the y value of 0, that I do get 4, and it does make the second equation true, so it satisfies both equations. So conceptually we see we just plot them on a graph and see where they touch. With technology, that's very easy. We won't always use technology though. We will have to do some of them by hand. So here's an example of how we do it by hand. Same order, and I do have the list of steps from before, just copied on the bottom here. So we first need to graph both of the equations that we're given. So the one in red is given to us in slope-intercept form. So we'll start at the y-intercept of 1. And then our slope is up 2 over 1. So I'm going to do as many of those as I can to make a really good line. And then we'll connect that line. So we've graphed the first line, which we already know how to do. Then we need to go graph the second line. Now that second line is in point slope form. So I know the point that was there was 2, -2, and our slope is -3/2. So if I start at 2, -2, the slope is -3/2, so I could go down 3 and over 2. But if I keep going that way, I don't think this is where the lines are going to touch. So I'm going to go the other way. So up 3 and over 2, up 3 and over 2. So I've graphed the second line. And now I can see where they touch. The point of intersection between those two lines, which I'm going to highlight here in green, is right there. So that's the answer. And this point right here seems to be the ordered pair of 0, 1. So we just want to make sure that it satisfies both original equations. So if the x value is 0 and the y value is 1, let's go plug that into the first equation, which was in red. So let's make sure that if y was 1, I would get that by taking 2 times 0 and adding 1. And that does work out, that 1 is equal to 1. So we're good there. We have to check the second equation. The second equation says the y value, which was 1, plus 2, should equal -3/2 of the x value, which was 0, minus 2. So here we get 3. On the right side, I'll simplify the parentheses first. And what's really nice about this one is dividing by 2 and multiplying by 2 are going to undo each other, and so will the negatives. So we do get that 3 is equal to 3. So the ordered pair of 0, 1 is the solution to this system because it satisfies both linear equations. So doing it by hand, also fairly easy. You just want to see where they touch. An important aspect of that, though, is when we do it by hand, sometimes we're going to run into some times where we can't really be sure. So for an example, I've brought up this system of equations. What you can see is one of the lines is given to us in standard form, and the other line is given to us in point slope form. We know how to graph both of these forms. So with standard form, it's best, according to our rule so far, is use the intercepts. So like the x-intercept is when y would equal 0. So the x-intercept is going to be 3. So in other words, I have the point 3, 0. So let's plot that point. Now we need the y-intercept for that line. So that's when x is equal to 0. So I'm going to see that the y-intercept was the value of 4. So in other words, the point 0, 4. So that point is right there. And let's go ahead and connect that line. Now the second equation is given to us in point slope form. So I know the point that is there was 5, -5, and the slope was 1. So the point 5, -5 is right here, and the slope is 1. So up 1 over 1. Now when I draw this line, this is our problem. I've accurately graphed both of them according to the rules we've learned in class, and I can see that they definitely touch. They touch right there. But I'm not sure what the coordinates of that is. Is that the point 6.5? Sorry, let me write that. Is that the point 6.5, comma, -3.5? Or is that the point 6.2? And the y value is more like -3.3. There's really no way we can tell. So here, we can't guess. So this is a situation like that. And what I'm trying to get at here is this intersection is not on grid lines. So we have to estimate. And it's not on a point that we placed. So those are the things we want to watch out for. If we can't tell exactly what the actual answer is, we can't guess. So what that means to us is when we're doing this by hand, in order to be sure that our solution is the exact solution, the point that we're going to circle as our answer needs to be a point that we actually plotted when we graphed the line by hand. So this means that when we make a graph, we need to plot as many points as possible. We need to fill up the graph with as many dots as we can so we can guarantee that we find the right one. What that'll mean, though, is there's some forms that are super easy to do, but if we want to get the most points possible, the easiest way to do that, right, getting more points on a line is using the slope, because the slope of a line allows us to find as many points as we need. So some things to bring up, like slope-intercept form is good to go, because we already have the slope in the form right away. So this is our slope, so we can use that to get as many points as we possibly can, and this is our starting point. Same thing with point-slope form. That one's good to go, because again, if we think about the form that's given to us, we already have a point that we can start with, which was x1, y1, but the slope is given. So if we need more points, we can just go ahead and use the slope to get more points. The thing that we'll need to watch out for is standard form. Standard form does not tell us the slope. Right? If I have something like 4x plus 3y is equal to 12, I don't know the slope of that line. And now, while I might be able to get 2 starting points, we want the slope to make a more accurate line to plot more points. So what we're going to do when we see standard form is we're going to convert to y equals form. Now I'm going to do that math in my head just for our notes today, but if I converted that, what I would get is y equals negative 4/3 plus 4. And once I convert that line, then again, we have a slope that we can use and we have a starting point. So it's just a small thing to watch out for when we're doing it by hand. So I have an example for us. When I look at trying to solve this system of equations, we have 2 lines, 4x plus 4y equals 20, and y equals 3x minus 3. The blue one, this is in slope-intercept form, so it's good to go. So I'm going to go ahead and just graph that. The y-intercept is negative 3. And I don't know where the point of intersection is going to be. So I'm going to use the slope of 3 to plot as many points on this line as I can. So I'm going to go up 3 over 1, up 3 over 1, up 3 over 1. I'm going to keep doing that until I run out of space, but I'm going to do it the other way too. I'm going to go down 3 into the left one. So I filled up the graph with as many points as I possibly can. Now, just as an example, the red one is not in the correct form. It's in standard form. If I tried to do it just by the intercepts, I would see the intercepts would be 5, 0 and 0, 5. And if I just plot those, so 5, 0 and 0, 5, when I draw that line, I'm not exactly sure if it's supposed to go through that point. Maybe when somebody else draws it, it looks like that. So what we need to be sure of to make sure we have the correct answer is we need to take that standard form of 4x plus 4y is equal to 20, and we need to get the y value alone. So we're going to subtract 4 x's. So we have 4y equals negative 4x plus 20, and then to get y alone, we're going to divide by 4. So we get y is equal to negative 1x plus 5. Once I'm in this form, I can plot many points because I now have the slope. So I'm going to plot as many points as I can until I exactly see the point of intersection. So if I started at the y-intercept, I go down 1 over 1, down 1 over 1. So right there, I just placed 2 dots on the same exact place. So I know for sure that this is going to be my answer because I physically placed 2 dots there. Let me draw my line a little bit straighter. It's a pretty bad line. So again, I don't want to be fooled by my visual representation, and I don't want to be fooled by our inability to draw straight lines, which is why we always want to plot as many points as possible. And as soon as I've seen that I've plotted a dot in the same place twice, that is going to be my answer. So the coordinates here are 2, 3. So the x value is 2, the y value is 3. And just to be sure that we didn't make any mistakes, we're going to check to make sure this is the answer. So if I plugged into the first equation, the x value is 2, the y value is 3, that should equal 20. So we get is 8 plus 12 is equal to 20, so we're good to go there. So it is a solution to the first equation, but if it's an actual answer to the system, it has to be true for both of them, which means the second equation also needs to be true. So if the second equation was y equals 3x minus 3, I can replace y with the y value I think it is, which is 3. And then the x value is 2, so what I would see is 3 is equal to 6 minus 3. So this is a solution to both equations in the system, which means it is a solution to the system of equations.